Okay, you will not be surprised to learn that this is waves 3. It's 3 of 5. What you might be surprised to learn is how short this one is. That's because this is kind of a conceptual one, and I'm going to try and keep it as short as possible. I may waffle on a bit, you'll just have to forgive me. This is diffraction. This is a wave spreading out as it goes through a slit. So a wave spreading out as it goes through a slit or around an obstacle is called diffraction. Spreading is the word. So here, because the length of the wave is very similar to the length of the slit, the distance between the two walls, then we're going to get almost perfect diffraction. And on the right hand side, it's behaving as if it was another source. So let's have a look at diffraction. That's diffraction coming through a slit, you can see, and here's another one. Now you're getting more diffraction on the right hand side because you have a smaller slit. So you get a more even form of diffraction. So the more diffraction if the size of the gap is similar or smaller than the wavelength. When you're diffracting round an obstacle, like a doorpost, you get a small amount of diffraction with a short wavelength. That's a short wavelength, light for instance. And this is sound, a longer wavelength. Yes, you get more diffraction. So, more diffraction if the wavelength is increased. So this spreading out happens more when the slit is smaller or when the wavelength is longer. Sound is much better at going round corners for this reason. So I've stilled it down here. This is diffraction being shown coming through there. You can see the wavefronts on the left with the troughs and the crests. They go through the hole and you get the spreading out. Now this diagram is important. The blue lines represent peaks. And diffraction works when the wavelength is about the same as the gap. But what if you have two holes? Well, if you have two holes, you have two places where they appear to be point sources. Now, that makes the two holes coherent because they're formed by the same waves. Why is this important? Because it proves that light is a wave. Thomas Young, brilliant scientist, 1805, wanted to prove that light was a wave. There'd been an argument between Newton and Huygens about whether light was a wave or a particle, and Huygens thought it was a wave, and he proved correct. Now, Young was able to prove this by using this experiment. He took a piece of glass, he blackened it in a lamp so it was completely black, and then he took his razor and drew two very narrow lines very close together. Obviously he had to do it a few times. And then he shone monochromatic light from a filter onto these two little holes, and both of the holes behaved as if they were coherent. So what I mean is they were in phase and they had the same frequency. So they both produced coherent waves. And where the peaks met, you got interference. So that red dot represents constructive interference, where the two peaks are meeting. So you get brighter light at those points. Everywhere that the peaks are crossing. Now, when a peak and a trough meet, you get darker because a peak and a trough are cancelling each other out and giving you destructive interference. Now, through the middle, where all the waves have travelled the same distance, we call that n equals 0 because there is a 0 difference in path length between waves from the top and waves from the bottom slit. However, this one is n equals 1. If you look carefully, you can see that the wave from the bottom has travelled extra wavelength in order to interfere with the wave from the top. It's gone one wavelength more. Similarly, there is a point on the other side where the top has travelled one wavelength more. So the 1 represents the fact that one of the waves is travelled exactly one wavelength more. Now, why exactly one wavelength? Because it's exactly so that a peak can meet the next peak and have constructive interference. And this will happen also when there's two difference. There are all the dots I'm producing now. They all have a difference of two wavelengths. So that's going to go out to the n equals 2 dot. So, interference pattern is then produced on a screen, which might be the end of the illustration or at the edge of the right-hand edge of the screen here that you're looking at, and you'll see dots, and the dots are called the interference pattern. A dot is a constructive interference. Dark spot is destructive interference. The whole thing's an interference pattern. It's caused by two coherent waves, and it proves that light is a wave. Here is it again drawn out by someone who knows more how to do it than me. You can see in this case the green dots are the constructive interference, and the red dots where the peak meets the trough, that is destructive interference. Here it is again as a slight animation. Right in the middle you can see peaks and peaks meeting to form bigger waves. And then before the next peak, you get a period where a peak has met a trough. They've interfered with each other. You can see that over the far left-hand side. And if that's happening, then you're getting destructive interference. You get still water. And that would be the equivalent of a dark spot on the screen. This is it slowed down so that it's a bit more easy to see. You can see the overlap. You can see where it's light in the middle of the wave, of the ray where the peaks are meeting, and you can see where it's dark, where a peak meets a trough and causes destructive interference. Here is it again. This is an original double slit experiment done by Young. Now we use a grating these days, but he used a double slit, and he got these fringes, which were bright and dark lines, really. That's what he meant by fringes. I don't know what's figure 5 from. I don't know what the first 4 were. Probably something even more boring. Did I say physics was boring? Huh! So, now we have to derive the equation for this so we can use it to work out the wavelength of light. Now, to do this, we have to use this. This is a wave. This is my attempt at drawing one anyway. As you can see, I could have done it better. In order to form interference, the peaks have to be together. Can you see that the peaks are on top, such as they are on top of each other? They're in line. So this means that down there, at the end of this, where we put the screen, there'll be a dot because a peak is meeting a peak, giving you constructive interference. That's constructive interference there, that dot. And there's a wavelength difference of 1. I can explain that in a moment. That angle, the angle we measure, that's theta. That distance, that's the distance that the top wave has travelled further than the bottom wave. That distance is a wavelength. That distance is the distance between the slits, d, and that's the wavelength at the top there, lambda. Let me find it. There. Now, what you're essentially looking at now is that there is a 1 wavelength difference between the two. If it was slightly less than a wavelength or slightly more, you wouldn't get constructive interference, and then you wouldn't see a bright dot. You only get the bright dot when a peak meets a peak. So that's exactly 1 wavelength. That's exactly 1 wavelength difference. And d is the distance between the slits. Now, for geometric reasons, the angle between the centre n equals 0 and n equals 1, which we call theta, is the same as the angle in that triangle. They're the same. Geometrically, it's just another one of these, mathematical things. But can you see that this is a right angle triangle and they are related by the sine rule? Because that lambda, the one that looks like a giraffe, the wavelength, is opposite the theta. So it's opposite over hypotenuse, and d is the hypotenuse. So sine, being opposite over hypotenuse, is lambda over d. Or to rewrite it on one line to make it easier to print before, modern text, we write it as, there, d sine theta equals lambda. D sine theta equals lambda. Now, this is all right for the n equals 1 dot. As you know, there's lots of other dots. So what's happening at the other dots? Well, at the other dots, where you have more than 1 wavelength, you have to insert a little n, because the distance, which we call lambda, could be bigger. It could be n lambda. That means there's more than 1 wavelength. Now, they're always whole numbers of wavelengths. So, for instance, at the n equals 2 dot, there is exactly 2 wavelengths difference. At the n equals 3, 3 wavelengths difference. Always has to be exact because the peak has to meet the peak. So we can have it for any n. And we can turn the formula into that again. So the spot on the screen, the constructive interference formed by the two peaks meeting, that can be written as a simple right-angled triangle. What you actually see, of course, on the screen is bright and dark. The yellow represents the light, the white is the screen background. So the very central line n equals 0, there is no difference between the path length of the two rays. But as we go out, you have 2n equals 1, which have one path length, 2n equals 2 that have two path lengths, and 2n equals 3 that have three path lengths. And this is called an interference pattern. So the bright lights are constructive interference, between them is destructive interference, the whole thing is an interference pattern. It's called by coherent light diffracting as it comes through two slits, and then interfering with each other as the two diffracted lights, which are coherent with each other, interfere with each other to form the interference pattern. As I just said, that 3 means there's 3 wavelengths difference in path. So the experiment, the measurement of the wavelength of monochromatic light. That's a laser, and that's a diffraction grating. We shine the laser light through the diffraction grating, and it falls on a meter stick. Now, the diffraction grating will have one spot in the middle where there is no path length differences, n equals 0. But then it will have n equals 1, and n equals 2, and n equals 1 and n equals 2 on the other side as well, because we can have a path length both sides. And what we do is simply measure the angles on both sides and find the average. And the way we find the angle is we measure the distance between the diffraction grating and the screen, and the distance between the centre dot and n equals 1, and we use tangent to find it. Find that angle, theta. There we are. Now, once we have the angle theta, and we know how many lines there are on diffraction grating, we can work out the wavelength of monochromatic light. This is the whole experiment here. Apparatus shown, nothing really interesting there, except for the thing of how you work out the distance d between the two lines in the diffraction grating. It's the inverse of what we call the grating number. This is the number of lines per millimetre. So if you've got the number of lines per millimetre, and you find the reciprocal of that, 1 over it, the reciprocal, then you find the distance between the lines in millimetres. Now you have to divide by 1,000 again to get the distance between the lines in metres before you put that in as the d in the formula. The theta you've calculated from your experiment using the tangent. You put the theta in, you find the sine of it, you times it by the d, you divide by the number you're looking at. So if it's n equals 1, you divide by 1. If it's the n equals 2 line you've got the angle for, you divide by 2. You repeat for all the different values you can get up to at least 3 and find the average value of lambda. Now the reason we take the line on both sides and find the average, the n equals 1 is on both sides, is we might not have put the diffraction grating exactly perpendicular to the ray. So there would be a slight angle difference between one side and another. But if you measure the two sides and find the average, you eliminate this problem. Now before we used the laser, we used to use this device. It's called a spectroscope. The right-hand side thing called the collimator, that would, or whatever it's called, it begins with a C, that thing over there, that used to get the light in a nice tight little beam, and it would hit the diffraction grating which was on the prism table, which is because usually you put a prism on it, and then you looked at it down the telescope so you could see it because it was usually quite small, and then you went, oh gosh, I can see it, oh I can see rainbows, oh fantastic. Nowadays, of course, very less impressive since the invention of the computer, videos, and a lot of other things which are a lot more impressive. This used to be impressive. This impressed me when I was a kid. I know, lasers hadn't been invented. They were just basically working on the wheel when I was a kid. Okay, so sort of the last section we have to deal with, and this is quite important as well. This is a very common question. It's actually more maths than anything else, really. If you look at the formula m lambda equals d sine theta. Did I say m? N. Anyway, n lambda d sine theta. Lambda is fixed. If you're just using red light, it's always going to be the same wavelength. So if you change the distance between the slits, d, as you can see in the diagram it's happening, you'll change the angle theta because nothing else can change. If d gets bigger, theta's got to get smaller. Now look at the diagram. As the slits move closer together, the angles increase and the fringes get further apart. As the d gets bigger, the angles get smaller and the fringes move closer together. So if you increase the number of lines per millimetre in a diffraction grating, that means the distance between the lines is less. The more lines, less distance. If there's less distance, you get a greater angle, and a greater angle means a lower percentage error. You get a better experiment. You get a more accurate result. Now, we don't say accurate result, we say a lower percentage error because, well, it's right and the other one isn't. So we usually say lower percentage error if we remember. Of course, the converse is also true. If the number of lines decreases, d will increase, theta will decrease, and you basically increase your percentage error. So the more lines per millimetre, the more accurate your experiment. This is your homework, and this is the end of the section. Short and sweet. Definitely need to listen to this again and see if you get it. If you didn't get everything the first time, try listening to it again. That's why I made it short. Some of the other ones, one listen, yeah. One listen at the beginning, one listen at the end, yeah. No problem. This one, 3 or 4 listens now, you might get it. Ha ha.